Welcome, everyone, to our final MIT Inside Track for Future Compute 2022. My name is Brian Bryson, and I'm the Director of Event Content and Experience here at MIT Technology Review. Today, we are talking about one of the most fascinating advancements that we've seen over the past years, and that is quantum computing. Back in 1981, MIT physicist Richard Feynman gave his first talk on quantum computing, theorizing that a computer can work under the principles of quantum physics. About a decade and a half later, researchers at Oxford, IBM, MIT, and Stanford stood up a working 2-bit quantum computer and demonstrated for the first time that it could solve a quantum algorithm. Push ahead another 15 years to 2016, and IBM put the first quantum computer on the cloud for anyone in the world to freely access and experiment with. Today, we're going to find out where things stand and what challenges remain to be solved before we start seeing quantum computers make an impact on our businesses and our lives. And with me to do this, I've got Steve Brierley. Steve's the founder and CEO of Riverlane, a company building the world's first operating system for error-corrected quantum computers, the problem which is arguably the biggest barrier to large-scale, reliable quantum computing. Steve has been in quantum for 20 years. He's an expert advisor to the UK government. Prior to founding Riverlane in 2016, he spent almost a decade at GCHQ as a senior research fellow at the University of Cambridge, leading major research projects in quantum computing. And he holds a PhD in quantum information from the University of York. I think we're in very good hands this morning. So good morning, Steve. Fantastic to have you join us here today.
Hey, Brian. Great to join you today.
So I look forward to the presentation, Steve. I'm going to cede the floor to you, and then we'll come back and dig into some of your material after that.
All right, thanks. I really love that you started with Richard Feynman as the founder of quantum computing. I'm going to talk a bit more about that. I'm going to start by talking about why quantum computing is so exciting, what it is that quantum computers can do. And then the second part of my talk, I'm going to explain sort of why is it that it's so hard to build a quantum computer, and what are the challenges that we need to overcome to get there. So I got fascinated by and obsessed by quantum mechanics when I was an undergraduate. I had more hair than I do now, and was really inspired by this theory of physics could explain so much. And this is really key to the applications of quantum computing. So I want to start with an analogy of how we use classical computers today in order to explain quantum computing. So we use computers to design new products in many industries. So in the aerospace industry, millions of hours of simulations on computers are used to design new airplanes. And these replaced the experiments that happened at the beginning of the aerospace industry. So the picture here on the left is at Kitty Hawk, the Wright brothers discovering flight through trial and error. But when we try to simulate the world at the level of microscopic systems, like atoms and electrons and proteins, we hit a wall. And so trying to simulate the way that a protein interacts with a potential medicine inside the human body, or the way electricity moves across a battery material, or the way that a catalyst reduces the energy consumption in an industrial process, is just impossible today. You know, even if we turn the entire planet into a supercomputer, we will never be able to solve these simulation problems. And the reason is quantum mechanics. The reason is that the equations of motion are too complex to solve with classical computers. And Feynman's great idea was that the only way to solve these equations would be to build a controllable quantum system, something that we could tune that would operate using the same equations of motion, and we could tune to the problem at hand. So this idea of building a controllable quantum system that Feynman proposed 40 years ago is now what we call quantum computing, and as a field is taking off rapidly. And I think the key to understanding where quantum computing will have a huge impact is really to look at those industries that were left behind by the first digital revolution. So quantum computers will start this era of human progress that is as significant as the first digital revolution. So the aerospace industry was transformed by ability to build computers to solve the equations of motion for flight. But now we want to build quantum computers to solve the equations of motion in healthcare, in manufacturing, and in climate change. And this will have a profound impact on how we develop new products in these industries. So I now want to talk about, like, how hard is it to build a quantum computer? Right, this is a huge challenge, and I think we have to be realistic about the magnitude of this challenge. It's something that is equivalent to landing on the moon. Right, we're not trying to build a 10% faster GPU device. We're trying to build an entirely new computer that operates at the level of quantum mechanics. And this is a huge engineering challenge. So I'm going to dig in a bit around the flavor of this challenge. I hope to give you a sense for what people are doing in the ecosystem and what we're doing at Riverlane. So the first thing is to say that there are many ways to build quantum bits, the basic building blocks of a quantum computer. So there are many viable paths here based on different types of physics. So there are atomic qubits. These are ion traps in neutral atoms. These essentially address individual atoms. There are superconducting qubits. I think you're going to hear a bit later today from IBM, who are building a superconducting system. There are qubits based on trapping individual electrons in semiconductor devices. And there are qubits based on sending individual photons through a waveguide, so through paths on a silicon wafer. I think the first thing just to recognize here is that this is absolutely astounding, right? That we could control a quantum system at this level, at the level of an individual atom or electron or photon. And that's really the huge progress that has been made, particularly in the last 2 decades. So the challenge here is that, unlike a classical computer, where the bit is represented by, or is representing a voltage on a wire, so there are millions of billions of electrons all in the same state. In a quantum computer, we have a single electron or a single atom that we're controlling. And so it's a very fragile system. And in fact, qubits are inherently noisy. The animation that's on the screen here shows the fluctuations in the vacuum, the quantum fluctuations in the vacuum. And this makes it very difficult to remove errors from the qubit. And in fact, qubits have, in effect, unavoidable errors. So we're at the level now where we can perform operations on qubits, perhaps 1 in 100, without any errors. But where we need to get to for this large-scale computation are billions and trillions of operations without error. Right? So that sounds like a massive gap, sounds like it's never going to happen, but it turns out there is a way forward. And that's called quantum error correction. So just like classical error correction, the idea here is that we spread out the information across many qubits so that if one of them fails, we can still recover the state of the overall system. And so quantum error correction borrows lots of the ideas from classical error correction. It turns out to be even more fascinating because of some of the constraints of quantum mechanics, like not being able to look at the state of the system without disturbing it. But this theory has been developed, and we understand a lot of the science behind quantum error correction. And the challenge now is to engineer systems that are capable of running error correcting codes during the computation. And this is really a huge engineering and classical information processing problem. So to implement quantum error correction during the computation, we need to process on the order of 100 terabytes of data per second. And so just to give you a sense of the magnitude, that's about the same as Netflix global streaming. And this needs to happen in real time. So between every operation on the quantum computer, we have to complete the syndrome readout, decode, correct cycle. So this loop is in effect the clock cycle of a quantum computer. And so it requires this huge amount of processing to solve these decoding problems during the computation, during the quantum computer, during the quantum computation. So this is a really large engineering challenge and is the central focus of Riverlane. So we are working on taking physical qubits and implementing quantum error correction to get to large-scale useful quantum computing. So in doing so, what error correction does is connect the qubits to the applications. So it's quantum error correction that enables these really exciting applications in quantum computing, whether that's drug binding affinity or the search for new battery materials or better catalysts, and so on. There are many applications that are enabled by large-scale error-corrected quantum computers. So I just wanted to finish by saying that there are really three problems that go into making useful quantum computing. So the first is to improve the physical system, to improve the qubits. And there are many companies in the world working on that, right? So reducing the error rates through better calibration, feedback, control, better material sciences, new ways of putting your qubit inside a dilution refrigerator, and so on. There are many core science and engineering challenges that are being addressed to improve the physical error rates. The second thing that needs to happen is to create this error-corrected fabric, and that requires us to perform rapid measurement, decoding, fast feedback, and that gets us to error-corrected quantum computers and large-scale computation. And then the final thing that I haven't talked much about, but I'm sure you'll hear more about today, is that we really need to seed the industries that will be transformed by quantum computing. And perhaps finish by providing an example from history. So Kodak famously invented the digital camera and decided not to pursue it because at the time it was rubbish, right, compared to their film cameras. It was 0.01 megapixels and really bulky, really heavy. And Kodak filed for insolvency at about the same time as Instagram and many industries or companies that had been formed on the back of digital photography. I think quantum computing is in very much the same position today. Quantum computers right now, they're not as good as your laptop, right? They're rubbish in comparison. But they're a new type of technology, and that will enable and create new industries, and there will be new companies built on quantum computing. So it's a very exciting time to be in the field, and I'm happy to take any questions. And so thank you.
Steve, that is fantastic. And I have lots of questions on how to prevent us from becoming the next Kodak and getting on board. So I think I want to start with something just a little more basic. So, you started off by talking about the equations of motions and some of the complexities that are just beyond the power of classical computing. So the domain of quantum computing, therefore, we're not going to be running PowerPoint and Excel on quantum computers. Can you talk a little bit about the industries that are really going to benefit? You mentioned aerospace, you mentioned healthcare. Who's going to benefit most here?
Yes, that's right. So we won't be using quantum computers to send email, that's for sure. And quantum will sit alongside classical computing. So for me, when we look at industries, the key thing is to think about the timing. So which industries are going to be impacted first? And that comes from understanding where quantum has an unfair advantage. So there are lots of things that quantum computers can do. Some of them, quantum computers do exponentially faster. So there's this huge advantage over using classical computing. And the reason that's important is because the semiconductor industry is, it's a huge industry. We've spent trillions of dollars building fabs and so on. It's a huge amount of investment. And so for quantum to outperform the semiconductor industry, it really needs these unfair advantages. So these are in the simulation of quantum physics. And if you look at industries where that could have a really outsized impact, it's those like the pharmaceutical industry. So the simulation of a protein and how it binds to an organic molecule. They are the materials industry. So there are plenty of materials problems across many areas. So even in the semiconductor industry, for example, you get, and then catalysis. So that's a big area where you're looking at industrial processes. So one example would be the fertilizer industry. So the way that fertilizer is produced is through a catalyst. And in fact, we know from comparison to how nature fixes nitrogen that there exists a better catalyst than we know how to build today, or a better industrial process than we know how to build today. But we haven't been able to develop that. And so simulation could help us develop better industrial processes in the pharmaceutical industry, or in the fertilizer industry.
Well, fantastic. So these are some major industries that affect everyone's lives. These are significant implications. So we need to get from where we are now to processing 100 terabytes per second. It was fascinating when you mentioned the Netflix volume comparison there. I guess the question is, we seem so far. It seems like there's so far to go on error correction to make this happen. What is it going to take? How are you going to do it, Steve? How are you going to correct and stabilize these qubits so that we can perform transactions and computations that we can rely upon?
Yeah, so the Netflix figure sounds scary, right? I mean, it's like a fraction of the global internet, and I'm saying we need to do that in a room, basically, like the computers in a room. Turns out that there are other problem areas where this has been done. A really great example is CERN. So CERN, the Large Hadron Collider, it processes about this much data, and that's actually the reason our VP of Engineering is Marco Ghibaldi. So he did exactly this at CERN. So the engineering and tech challenges have all been solved before, but in other contexts. So processing this much data has been done before at an experiment like CERN. Error correction is used all the time. For example, in the automotive industry, error correction is used regularly. So dedicated silicon that uses error correction has been built in the automotive industry. And maybe another good analogy is sort of AI. So dedicated processors and chips are being developed for the AI industry, basically really great matrix multipliers. So I think this kind of technology challenge is very much solvable with, or this kind of engineering challenge is solvable with technology we have today. It's just that we need to do this in quantum computing. So we need to do it for this specifics of the quantum error correction problem.
Now, is your quantum correction happening on classical computing, or is it quantum that's actually doing the error correction?
Yeah, so it's on classical computers.
Okay.
So yeah, the quantum qubits, we read out some syndrome data. This basically gives us a clue about where the errors happened. And then we have to solve this kind of Sudoku type puzzle, this decoding problem very, very quickly. And then that allows us to guess, like, where did the errors happen? And if we're right, then great. And the computation carries on error free. If we make a mistake, then the whole thing breaks. So we have to be very quick and very accurate.
And you have to do this without observing the data, because that would disrupt the quantum state. Is that
Yeah, so that's a really fascinating thing, that you can do that. So you can measure just the effect of errors without seeing anything about the current state of the quantum computer. So you can see that an error has caused something to happen, but without seeing the overall state of the quantum computer. I don't think this is obvious at all, that this is
It's
possible, and I think it's a
it's
key, it's like a
fascinating
really
and it's
key bit.
mind-bending. It's amazing, but I completely understand what needs to happen here. You need stable qubits to make the calculations to get these computers to where we need to be. Steve, we're coming up on our time, but I want to just jump straight ahead. So here we are today. It's 2022. We've got quantum computers. People are building various types. You're working on error correction. How long before this has viable commercial application, do you think?
Yeah, so I think we're going to see a staging of applications. So we'll see the first big demonstration of quantum outperforming classical systems within the next 4 to 5 years, and then it's perhaps by the end of this decade that that translates into something really commercial. So this is a long journey. Like there's a lot to do, but I actually think this is really a function of how hard we try, to some extent. How much engineering power we bring to bear on this. And so I would say, for all of your listeners, there are a lot of really great problems to solve. You don't need a background in quantum computing to come and help solve these problems. If these kind of engineering problems are exciting, then get in touch. We can make this happen sooner.
Everyone, Steve Brierley, founder and CEO of Riverlane. Great stuff, Steve. I think we all very much appreciate your insights into this fascinating technology and new ways of computing.
Thanks, Brian. Great talking to you.